And hello friends, welcome to today's video on Labview. Welcome. So today we're going to carry on where we last left off, and I want to say again that there are a number of things you can do with your signal once you spectralize it. There are Labview ways to process some of the signals using like a high and low pass filter. I can talk about that much later, but first I want to get past the point of how do you read this fast Fourier transform graph, and why does it not correspond? Why does this frequency bin at the bottom not correspond to actual hertz? Okay, or how do you actually get it to correspond to actual hertz? So let's load up that C note again. It's playing. I might use a different note in future, but okay, so you notice again in your power spectrum you are able to see all the relevant frequencies at about let me change this to there. You can see one big peak at 132-ish hertz. Okay, another one at about 264, another one about 396. So that this is correct. But when you see this, when you kind of zoom in to this fast Fourier transform, you'll notice something. Your left and right are actually symmetrical, because one actually deals with the positive part of the sine wave. The right side deals with the negative part of the sine wave. So that's something just to note for fast Fourier transform graph. The left side actually corresponds to the positive part. The right side corresponds to the negative part of the sine wave. Okay, so you just need to read one side of this graph and that will do. Now, if I switch this to, let's say, the same frequency bandwidth, maybe 400, you will see some peaks here. If I switch it to maybe 1000, you'll see another few peaks. Okay, 1000. Yes, you will see another few peaks. And if I change it to about 8000, you'll notice that we have a characteristic peak structure, but you'll notice that this peak actually starts to hang out at around 800. Okay, you can see this is about 800. So I zoom into the peak below 1000. Okay, the biggest peak is over here around 850. But you see the C note is not 850 hertz. So this is around the frequency bin 850. So what's the deal with that, right? How then could you make this frequency bins at the bottom correspond to actual hertz? Okay, so that's something we want to start talking about this video. Okay, so one clue I have for you, okay, is to set the Fft size. Okay, set the Fft size to 44100, and you'll see some magic that actually occurs. Alright, so under your FFT-VI, you will see one that says Fft size. So go to that Fft size in your block diagram, right click, and you can create a control, and then you will see this Fft size. Now the long and short of it is that the Fft size is the size of the array that you want to do your FFT on. So okay, let's say you have a very long matrix of values, x1 or x0. You usually like to start from 0 in this case, and then x1, and you go all the way to x of n minus 1. So this is actually n elements in this matrix. So yeah, let's say you have n values inside this matrix which you want to do a Fourier transform. Okay, the Fourier transform will be basically shifting, okay, the n elements of this matrix into a new matrix which is also having n elements. So you do your fast Fourier transform. Okay, fast Fourier transform, and then you put all of these into n frequency bins. So f0, f1, ... to fn minus 1. Okay, so what is this FFT size? The FFT size is basically how many elements are you trying to do your Fourier transform in. Okay, so let's say you have a matrix of size. You have a matrix of size n, but you key in your FFT size of, let's say, 8. If you have 8 elements, okay, I'm not drawing to scale, but if you have 8 elements, then what Labview will do is to take the first eight elements of this matrix and do a Fourier transform here, and then it will have a new matrix of about 8 elements. So let me demonstrate. So you only take in the first 8 elements. So let's try the FFT size of 8. Okay, so when you make the control, it will pop up over here, this FFT size thing here, and then you will have really 8 frequency bins. So from 0, 1, 2, 3, 4, 5, 6, and 7. Okay, so there will be 8 frequency bins over there. Okay, so that is what the FFT size does. Now, if you actually put in 0 or minus 1, what Labview will do is to say that if you key in 0 or minus 1, Labview will take the fast Fourier transform size to be the size of the matrix that you put in. So that means all of the values kind of get keyed in. So if you get 0 or minus 1, it will kind of give you the same results. You will actually see it in the Labview help. So if you go to show context help, go to FFT, you click this thing called detailed help. Okay, I'll show you again. Click this yellow question mark here, show context help window, hover over the FFT, and then you click detailed help. Okay, then you have a window that pops up like that. Okay, this is a local help file. You see this is actually stored in the user local blah 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 file. For Windows it may be slightly different, but this is on my Linux machine. So this is what it will be like. Okay, so you look at this thing saying FFT size. Say FFT size is the length of the FFT, fast Fourier transform, that you want to perform. If the FFT size is greater than the number of elements in X, for example, this VI adds zeros to the end of X to match the FFT size. So what are they talking about? Okay, so if you have an n size matrix, but your FFT size is maybe m plus 500, okay, it will actually just lengthen the matrix and you just give it a bunch of extra zeros at the back. Okay, so it will just lengthen the matrix and add a bunch of extra zeros at the back, and then it will calculate the FFT, fast Fourier transform. So that's how this works. Why would you want to do that? Usually it's because FFTs, they work best when you have integers, when you have the size of the matrix in powers of 2 to the power of n, or 2 to the power of alpha, where alpha is some integer. Okay, so if fast Fourier transform works best in this with 2 to the power of alpha, where alpha is some integer. Okay, so that's why you might want to make n bigger than your FFT size, bigger than your matrix size. But don't worry, even if you just left it as the default as 0 or minus 1, such that Labview will take the default matrix size n, or the default array size n, as your FFT size, that is still okay. As you saw, it was still able to produce a spectrum. Okay, so now one special thing. Okay, so yeah, I mean, I've gone through the FFT size, and of course, okay, over here it says if the FFT size is less than or equal to 0, this VI uses the length x as the FFT size, which is what I was talking about just now. So that's how this thing works. Now this part I will go through a little bit later. All right, so how do you get the frequency bin to correspond to actual hertz? Now I want to give you something interesting. Now when I switch the FFT size to 44,100, this is a very special number, especially for audio files. Okay, so now we will have this fast Fourier transform. and I will actually switch it down to 1000 Hertz. Now notice where the peaks are. When I switch the FFT size to 44100, I'm only taking the first 44100 samples and perform a fast Fourier transform. Notice that the frequency bins at about 130, there is a peak here. Around 260, there's another peak. Just below 400, about 396, there is another peak. So let's switch it to 150. And you can notice the peak is at about 132 Hertz. Or the 132nd frequency bin. And that actually corresponds to some Hertz or what have you not. So you notice that when you have, I can change the scaling by switching these two numbers. But notice that once you change it to 44100, the fast Fourier transform size, the frequency bins actually now correspond 1-to-1 in a unit conversion, so to speak, 1-to-1 according to actual Hertz. Okay, so what is going on here? Alright, so if you take a look at the Labview help, you will see how the FFT is being performed. Okay, so this is a Fourier transform is usually done in integrals. Alright, Fourier transform is usually done in integrals. But since we are doing a discrete Fourier transform, we don't have a continuous function. We use a summation instead. So this is what this formula here is talking about. If you want to know more, you can take a look at this video by Steve Brunton. Okay, so it's a very good. He explains it very well, this fast Fourier transform. I'll leave it in the link below. So now I'll give you some intuition on what this fast Fourier transform is about. That's very important that you go and take a look. So I'll not go through too much of that. Alright, but I'll explain how the FFT stuff works. Okay, look at this. Okay, very important note here. Okay, the frequency resolution or the frequency spacing between components of Y, where Y is the matrix of the Fourier transform. So remember, we had an initial matrix of values x0, x1. Okay, got ... and then xn minus 1. Okay, and then we swap it to a frequency bin. So this is frequency bin 0, frequency bin 1, then you go all the way down to frequency bin of n minus 1. Okay, so this is what's going on. Alright, now when I switch it to 44100, why does the frequency bin correspond to Hertz 1-to-1? So well, this one is the answer. It says the frequency resolution or frequency spacing between components of Y, meaning to say that the change in frequency, the change in frequency from, let's say, F0 to F1, the delta F here is the formula given is Fs, which is the sampling frequency, over n. This n here is the FFT size. So n is the FFT size. So it's not this n. So I should use a different n. I should use FFT size. So what is this FFT size? The FFT size is the number that you key in here. Now, when I key in this FFT size to be 44100, what happens? So taking a look at this formula, this is Fs over FFT. So remember the spacing between each frequency, right? Between each frequency, it's Fs, which is the sampling frequency, over FFT size. Now, if I happen to make my sampling frequency and FFT size the same, i.e. to say, if I have a 44100 over 44100, that means my sampling frequency must be 44100, right? If I make the sampling frequency equivalent to the FFT size, delta F here is exactly 1 Hertz. So that means if I go from frequency bin 0 to frequency 1, the difference is exactly 1 Hertz. So that means if I go from frequency bin 100, this corresponds to about 100 Hertz. The frequency bin at 130 corresponds to about 130 Hertz. So if you do exactly like so, you will only take the first 44 100 samples. So, but if your sampling rate is 44 100 Hertz as well, then the spacing between each frequency bin will be 1 Hertz. So at the bottom you will be able to see your what do you call that? Your sampling rate. I mean your frequency bin will correspond to number of Hertz in a 1-to-1 correspondence. Okay, so you can see the peaks here at 130, 264 and 396. Very similar to what we have in the power spectrum, right? Of course the power spectrum is different, but you can see at least the peaks are at the same place, and that's important if you want to check what the frequency is. After all, we are interested in the frequency analysis. Okay, so how then is this going to work if you have more samples than 44 100? And how did I even know that the samples are the samples are being sampled at a rate of 44 100 Hertz? The sampling frequency is 44 100 Hertz. How did I know that? And what on earth is sampling rate anyhow? Okay, so these are some of the questions that you may have. Okay, so I will have to take some time to explain some of them. If you're not sure, if you already know what all of these are, you can just skip ahead. If not, you can just continue watching. Okay, so this is the very useful website that I want you to take a look at, and this actually gives you some very good insight into what sampling rate is. Okay, so let me first answer the question, what is sampling rate? Okay, sampling rate, okay, is like something like this. Okay, so let's say you have a sound signal, right? So you have some amplitude versus time, and your sound signal very simplistically can be a sine wave, right? Alright, so very simplistic, the most simple sound wave you can think of is perhaps a sine or cosine wave, as you are seeing here. Alright, so this is something we call a continuous. Okay, this is a continuous signal. Okay, it's a continuous signal because the amplitude is actually continuous and the time is continuous. Another name that we use is, this is called an analog signal. Okay, so however, we cannot store analog signal as well in let's say a computer. For some reason, if you try to record and store analog signals, there may be some distortion due to the electrical circuitry of the thing. There may be some distortions here and there. So to overcome this, they use digital signals. Okay, so what are digital signals? Now, digital signals are basically they do this thing, right? Okay, so let's say your sine wave is go from 10 to minus 10, right? So this is how digital signals kind of works, and this is how sampling frequency kind of works. If your sampling frequency, let's say, is 1 Hertz, all right, okay, or 0.1 Hertz, and then let's say your period here is 1 second. All right, so we have the first hump of the sine wave being over here 1 second. So this is a okay, we have a sampling frequency, let's say, of 10 Hertz. 10 Hertz. So that's 10 times per second, not 0.1 Hertz. So this period is about 2 seconds, or this analog signal is 0.5 Hertz. Okay, so let's say at t equals 0.1 seconds. Okay, or t equals 0 seconds, it will sample like so. It will read the signal here. It will read the signal here, and it says that the amplitude is 0. Okay, at t equals to 0.1 seconds. T equals to 0.1 seconds. Yeah, I think I'm running out of time soon. T equals to, let me see. Let me give it 2 more minutes. T equals 0.1 seconds. It will sample this much. Okay, it will sample this amplitude here, and then it will hold. Okay, and this may be somewhere like 0. Your actual analog signal may be 0.4467. I don't know what the numbers are. I'm just making this stuff up. But sometimes your digital signal will actually force it to maybe somewhere between 0.4 and 0.5. So your amplitude will not be recorded as 0.4667. It will the sampler will read, okay, 0.4667 is closer to 0.4. So let me record this value as 0.4, for example. So it will actually record a signal at 0.4 until the time equals to 0.2. At time equals 0.2, it will read the analog signal again, and then it will sample another piece of data, and it will hold for another 0.1 seconds. So what happens after a while? Okay, pardon me for that. Let me switch it to silent mode. So annoying. So after a while, you will have something that approximates the waveform that you see. Okay, so you'll have sort of a bar chart that samples the waveform that you see here. Okay, and this is what basically what digital time's up. This is what sampling rate is about, and that actually helps to convert from an analog signal to something more like a digital signal, where time is either 0 or 0.1. It cannot be something in between. So these things are called discretized values of time, and you also have discretized values of amplitude, for example. So I don't know what these values are. I'm just making this stuff up. But at the end of the day, you will have something like this bar chart. So how often are these bar charts so-called recorded? Okay, they will be recorded according to the sampling frequency. Of course, the higher your sampling frequency, the closer your bar charts will resemble the actual analog wave. And for sound frequencies, your standard sampling rates are about 44.1 kilohertz. Okay, or you can switch it higher for higher fidelity audio. So maybe in the next video I'll demonstrate a little bit more, but hopefully this is insightful into what sampling rate is about. Okay, so hopefully that clears up some confusion. Thanks for watching. I'll see you guys in the next video.